Dear participants, just give us 1-2 more minutes. We are starting soon.
Okay, madam.
Good evening, respected dignitaries and dear participants. On behalf of Department of Information Technology, Techno International Newtown, I, Dr. Taposhi Bhattacharjee, Coordinator, along with my co-coordinator, Dr. Kamalesh Kormokar, warmly welcome you all to the AICT ATAL Academy approved 6 days online faculty development program on emergence of cloud computing, cloud technologies, and recent trends. It will be held from 13th to 18th January 2025. The timings are from 6 p.m. to 9 p.m. from Monday to Friday and 2 p.m. to 8 p.m. on Saturday. The FDP on emergence of cloud computing, cloud technologies, and recent trends focuses on understanding the growing role of cloud technologies in modern education and industries. Participants will explore fundamental concepts, advancements in cloud services, and recent trends. This program aims to empower the participants with the knowledge to leverage cloud computing effectively in teaching and research domains. Without further ado, I'd like to call Professor Saurabh Mohapatra, HOD, Department of IT, Techno International Newtown, to deliver a welcome speech. Over to you, sir.
Very good evening to all the respected dignitaries present here. It is with immense pleasure and honor that I extend a warm welcome to our distinguished guests and esteemed speakers for today's session. I extend a warm greeting to everyone attending this faculty development program on emergence of cloud computing, cloud technologies, and recent trends. The topic for this FDP was selected from a pool of over 4,500 applicants, and we are proud to say that our proposal was one of the 500 that was chosen, and total participants of 320 throughout the India. We are delighted to have with us Dr. Arindram Rai, Executive Director of Techno India Group. Dr. Roy's leadership and vision have been pivotal in shaping the landscape of educations and technologies. And we are privileged to have him with us today. I heartily welcome Dr. Arindam Rai in this session. We have with us Dr. Ayan Chakraborty, Principal of Techno International Newtown, whose leadership and commitment to the academic excellence are truly inspirational. And we are delighted to listen few words from him in our sessions. A warm welcome to Dr. Chakraborty. Dr. Sagata Pal is also with us, who is the IQAC coordinator and academic coordinator of Techno International Newtown. Dr. Pal's dedication to quality educations and continuous academic information improvements is truly commendable. And we are grateful to have him here with us today. Welcome, Dr. Pal. Professor Shoma Chatterjee Ghosh is also with us, Assistant Registrars of Techno International Newtown. Professor Ghosh supports and organizational insights have played a crucial role in making this event a success. We are excited to have here with us. Welcome, Shoma Madam. We have with us Dr. Nandini Mukherjee, professor at Jadavpur University. Professor Mukherjee's expertise and academic excellence are well known, and her presence adds tremendous value to this event. Ma'am have a sessions also today. We are welcoming ma'am for these sessions. Now I'm telling something about this program. This faculty development programs is basically aimed to provide an in-depth understanding of the emergence of cloud computing. Here we can explore the latest technologies and discuss the trends of shaping the futures. I'd like to take this opportunity to thank our esteemed speakers and resource persons for sharing their expertise in the coming 6 days. Their contributions will undoubtedly enrich our understanding and help us to explore new horizons in cloud computing and its applications. I encourage all the participants should engage actively throughout the sessions. They should share their experience and collaborate with others to enhance the efficiencies in that field. Together, we can unlock the full potential of cloud technologies and contribute to the advancement of knowledge through these sessions. Once again, a warm welcome to all of you, and I look forward to a fruitful and enriching experience over the course in this program. Thank you. Thank you all. Again, I am welcome all the participants here. Thank you.
Thank you very much, sir, for this warm welcome. Unfortunately, due to some unavoidable circumstances, Dr. Shonku Bose, Chief Executive Officer of Techno India Group, is not available for this inauguration session. However, he has shared his good wishes for the FDP. He will address the participants in any of the coming sessions. Now, it is my extreme privilege to introduce Dr. Arindam Roy, Executive Director, Techno India Group. Sir, please share your valuable thoughts with us. Sir, you are not audible. I think you need to switch on your audio.
Is it all right?
Yes, sir.
Yes, sir.
Good evening, respected expert members, esteemed speakers, valued participants, distinguished faculty, and dear colleagues. It's my great pleasure to welcome you all to this week-long AICT-sponsored online faculty development program on emergence of cloud computing, cloud technologies, and recent trends, organized by the Department of Information Technology, Techno International Newtown, Kolkata. I am delighted to see such enthusiastic participation from faculty members across the country in this program, which is aimed at enhancing your knowledge, expertise in one of the most transformative fields in modern technology. The FDP comes at a pivotal time when cloud computing and technologies have been reshaping this landscape of data storage, offering new ways to teach, learn, and innovate. It is well known cloud computing has revolutionized the computing infrastructure, data storage, and service delivery. As technology evolves rapidly, it is essential for educators, professionals to stay updated with the latest trends in cloud technologies, ensuring they cannot only impart relevant knowledge to the students, but also leverage these technologies to improve their own professional efficiency. This FDP will provide you with an in-depth understanding of cloud computing concepts, cloud-based services, emerging trends, and how these technologies are being applied across different industries. It will also introduce you to the most recent innovation in cloud technologies, helping you develop a broader perspective in the future of computing. By the end of this FDP program, we hope that you will gain an in-depth understanding of cloud computing, explore the key trends in cloud technologies, understand the security challenges and solution in cloud environments, learn about the practical applications of the cloud technologies in different sectors, including education, healthcare, business, etc. We are grateful to AICT ATAL Academy for their continuous support and vision in enhancing professional development across the country, which will ultimately be beneficial for future technologists. Their sponsorship exemplifies their commitment to enabling transformative educational experiences which help in bridging the knowledge gap teaching to reorient new skills sets among the students. I would like to thank the subject experts, scientists from Calcutta University, Jadavpur University, Maulana Abul Kalam Azad University of Technology, San Diego Supercomputer Center, USA, and UIU Vietnam industry experts from CDAC, TCS for their valuable contributions and for taking time to share their acumen with all of you. My heartfelt thanks to all of you, the participants, for showing interest in this FDP. Your participation demonstrates your commitment to continuous learning, unlearning, and enriching professional development. I would like to commend the Department of Information Technology, Techno International Newtown, Kolkata, for their exceptional efforts in organizing this event. Their dedication to academic excellence and commitment to stay at the forefront of technological innovation is truly inspiring. Special thanks to Dr. Taposhi Bhattacharya, coordinator, Dr. Kamalesh Karmakar, co-coordinator, for organizing this FDP. It would be wrong if the contribution of Professor Saurabh Mahapatra is not mentioned. Finally, I convey my special thanks to Dr. Ayan Chakraborty, principal, who has been leading the team. Let us make the most of this opportunity to learn, collaborate, and innovate together. Once again, I warmly welcome you all and look forward to an engaging and fruitful 6 days ahead, wishing the FDP a grand success. Thank you all. Namaskar.
Thank you very much, sir, for your inspiring words. It means a lot for us. Now, please join me in welcoming our respected principal, Dr. Ayan Chakraborty. His guidance, endless support, and constant motivation have helped us to make this FDP a reality today. Sir, we are eagerly waiting to hear from you. Sir, please share a few words with us. Sir, principal sir.
Oh, sorry, my microphone was muted. Am I audible?
Yes, sir, you're audible.
Am I audible? Okay, okay.
Yes.
Thank you. Good evening to all of you, all the participants, and especially today's speaker, Nandini Madam from Jadavpur University. With her profound experience in this domain, we will be enlightened for today's session. And my heartfelt congratulations to the Department of Information Technology, the coordinators, Professor Bhattacharya and Professor Karmakar, along with HOD Professor Saurabh Mahapatra, to organize this beautiful session for this week-long session. And this time, for this academic year, TINT is focused, especially focused on the FDP, or the faculty development training, to organize more faculty development training. And basically, we are very much, we are giving emphasis on attending different hands-on and training sessions for the faculty members, especially for the faculty members in outside TINT also. So this opportunity has given by All India Council for Technical Education, AICT, along with ATAL Academy. And we are very much privileged. We feel very privileged to get this opportunity from AICT and ATAL Academy, so that TINT and Department of Information Technology has got the chance to organize this week-long development program, faculty development program on cloud computing and its recent trends, emergence of cloud computing with its recent trends. Some new domains. This cloud computing is not so new, but still we feel that in our university curriculum also, this cloud computing has already been included. And furthermore, TINT has a very enriched pipeline for research, innovation, and incubation. We are inculcating this ecosystem in TINT for last 5 to 6 years. And we feel that when the mentors or the guide for different projects, we got funding from different central government and state government organizations. And when we are going to guide or mentor the students for these funded projects or publishing the papers on these cutting edge technologies, we strongly believe that, we strongly feel that the training is first the training to the faculty members, straight to the trainers, what we can say. The training for the faculty members on these cutting edge technologies, which includes cloud computing, ubiquitous computing, now it is HPC, high performance computing, and recently, very recently, AI/ML machine learning along with quantum computing. All of these budding domains, the knowledge on all of these budding domains are very much required. We feel that when we are going to guide our students for different externally funded or government funded projects. So this time is a very important juncture point when the Department of IT is going to arrange, along with the help of ATAL Academy and AICT, this week-long faculty development program on cloud computing. So I wish every success and a grand success with all the distinguished speakers from whom we are going to be enlightened. We are going to get the answers of very untold or sometimes very frequently asked questions, our confusions for this from this training session and from this faculty development session. And I can see at the end of the working hours, the enthusiasm is prevailed to all of these huge number of participants has already joined here. I can see the number is right now 191 plus, it's touching 200. So really appreciable. And we are really very much thankful to all the participants from all over India to join in this program and to leverage us the scope to serve them with this FDP program. Thanks to Dr. Arindam Roy. He is always shows us the guidance and the path uh, for the units, different college and university units of Techno India Group. His vision is always a torch in front of us to enlighten our path. And we all miss Dr. Shonku Bose, our group CEO, Techno India Group, uh, who is being an administrator, is like to be known as academician more. Just few days back, another Vani program, AICT funded Vani program, only 3 colleges in West Bengal has got the scope to nurture this, to stage this Vani program, and TINT is one of them. Department of Computer Science Engineering has organized this Vani program. There also we see the enthusiasm in between the participants from different college, different faculty members. Though we all know that throughout West Bengal, university examination is going on. University semester examination is going on. So uh, after continuing the working day, whole working day with invigilation, script checking, still at the end of the day, from this evening, they have that enthusiasm within them. That's why this almost 200 participants are here. We are very much grateful to all of them. And thank you very much for presenting this FDP on behalf of Department of Information Technology, Techno International Newtown, to the outer world. And we hope that this FDP will create a good impact on the teaching learning, outcome-based teaching learning, where this what I have started with, the project, more attracting more funded projects, involving in research, student publication. It will help a lot. Thank you very much. Thank you, the organizer, giving me this platform. to say these few words. Thank you. Thank you so much. We are eager to hear from our today's distinguished speaker, Nandini Madam. Thank you.
Thank you, sir. You are always an inspiration to all of us. Next, it is my privilege to introduce Dr. Shagoto Pal, IQAC and Academic Coordinator of Techno International Newtown. Sir, please share your thoughts with us.
Hello, am I audible?
Yes, sir.
So, good evening, all the participants, the resource person, the organizers. This FDP, that is ATAL FDP, ATAL FDP is AICT's Training and Learning Faculty Development Program. Actually, it is aimed or the objective of this FDP is to provide quality training, develop leadership skill, promote community well-being, develop career skill, improve communication skill, develop teaching skill. So this FDP, I think, will help all the teachers, those who are with cloud computing or related domain, to improve their skills, as well as for the new teachers, they will learn lots of things from this particular FDP, as we have a very strong pool of resource person. Regarding cloud, it has the benefits, the well-known benefits like scalability, cost reduction, data backup, and disaster recovery, access to tools and services, collaboration and remote work, faster application development, etc. So along with this, there are more benefits of cloud computing that we learn from the resource persons. Mainly in the market, there are three well-known platforms available. One is Google Cloud, that is Microsoft Azure, and that is AWS. AWS has a facility that is called AWS Academy that we can use in educational organization to give the course materials and all, which are free, and they also provide us opportunity to get the certification from AWS with a reduced cost. With this, I end. Thank you, Taposhi Madam. Thank you, Kamalesh Sir. Thank you, Saurabh Sir, for inviting me in this session.
Thank you, sir, for your warm words. Now, we are eager to hear from our respected Assistant Registrar Madam, Professor Shoma Chatterjee Ghosh. She has supported us a lot for this FDP. Madam, please share your thoughts with us.
Thank you, Taposhi. Am I audible, firstly?
Yeah, yes, you are audible.
So, good evening, everyone. It is a great honor to welcome you all to this one-week online AICT training and learning program on emergence of cloud computing, cloud technologies and recent trends. This program brings together expert speakers from around the world, which we can see, to share their knowledge on the latest advancements in cloud computing. As teachers, it is very important for us to stay updated with these new technologies. So this kind of program is designed to not only increase our understanding, but also help us to teach students about responsible and effective cloud practices. And I believe this FDP will generate new ideas, encourage collaborations across disciplines, and strengthen our role in advancing technology-driven education and research. I extend my gratitude to our distinguished speakers for sharing their time and expertise. Thanks to AICT for choosing our institute amongst that 4,500 institutes across India. Thanks to the Department of Information Technology for arranging this program. Thanks to Dr. Taposhi Bhattacharjee, Dr. Kamalesh Karmakar, and Dr. Saurabh Mahapatra for the smooth coordination. And lastly, I encourage all the participants to make the most of this enriching experience. Thank you so much. Thank you.
Thank you, ma'am, for such motivating words. We are privileged to have one of our esteemed speakers with us in this inauguration session. She is none other than Professor Dr. Nandini Mukherjee, Professor, Department of CSE, Jadavpur University, Kolkata. We will be listening to her speech after this session only. But before that, I'd like to take this opportunity to request ma'am to share a few words with us. Ma'am, please.
Thank you, and good evening to all the participants and all the dignitaries who are present during this inaugural session. Actually, I'm going to speak just after the inaugural session, so nothing much to say now. I would like only to welcome all the participants and hope they will enjoy this 6 days program and will learn a lot regarding cloud computing and other aspects of cloud computing. Thank you very much.
Thank you, ma'am. Finally, we have reached to
madam.
the very last phase of the inauguration session. I'd like to call Dr. Kamolesh Kormokar, co-coordinator of the FDP, to conclude the session. Over to you, sir.
Good afternoon, everyone. It is my honor to deliver the closing remarks for this inspiring inauguration session of this faculty development program. Today marks the beginning of a journey. The challenges we face in this dynamic academic landscape are immense, and so are the opportunities. This program is a platform to not only enhance our knowledge, but also to foster the creativity and adaptability needed to navigate these challenges effectively. First, I would like to thank all the eminent speakers who will deliver their lectures in these upcoming sessions during this next 6 days. Thanks to Professor Dr. Nandini Mukherjee for the inspiring speech in the inaugural session, and she was my guide during my master's degree. I would like to thank Mr. Sottam Rai Chaudhuri, Managing Director, Techno India Group, Dr. Shonku Bosch, Group CEO, Techno India Group, and Dean, Sister Nivedita University, Dr. Arindam De, Executive Director, Techno India Group, Dr. Ayan Chakraborty, Principal, Techno International Newtown, Professor Shoma Chatterjee, Assistant Registrar, Dr. Shagoto Pal, Coordinator, IQSU, Professor Saurabh Mahapatro, Head of the Department of IT, and the members of Advisory Committee and Organizing Committee, whose dedication and hard work have made this program possible. Over the next 6 days, we will delve into the emergence of cloud computing, exploring new methodologies, tools, and perspectives. This is an opportunity to exchange ideas, share experiences, and build collaborations that extend beyond the boundaries of this program. In conclusion, I encourage each of every participant in this program with an open mind and eagerness to learn. Let us take the insight we gain here and translate them into the meaningful changes in our classroom and institutions. Thank you. I wish you all an engaging and fruitful faculty development program. So let's move forward with optimism and dedication. Thank you once again, and let's begin our journey. Thank you.
So I'll request all the participants and respected dignitaries to switch on the video or camera just for 1 or 2 minutes. We need to take few photographs. Just it's a formality, just 2 to 3 minutes maximum we need for that. Respected dignitaries and dear participants, please switch on your camera.
Good.
Okay, done. It's done from our end. So we will be joining to the very first session of the very first day. Actually, Next two sessions will be taken by Nandini ma'am. So she's already there. Ma'am, we be taking a break of 5 minutes, or the participants will stay here and start?
I am okay. I mean, if
Okay, so I think we are already out of time. So ma'am, you can start like sharing. Before that, let me introduce ma'am. Actually, ma'am doesn't need any introduction, but still, it's a like Professor Dr. Nandini Mukherjee received her PhD degree in computer science from the University of Manchester, United Kingdom in the year 1999. She joined as a faculty member in the Department of Computer Science and Engineering, Jadavpur University in the year 1992. In 1996, she received a Commonwealth Scholarship tenable in the United Kingdom. She became a professor at Jadavpur University in 2006. Her research interests are in the areas of high performance parallel computing, grid computing, mobile computing, and many more. She is a senior member of IEEE. I don't know, ma'am, I'm allowed to say these things for you or not. I'm very honored to introduce you in this platform. Ma'am, please, you can share your screen, and over to you, ma'am.
Thank you very much, Taposhi, for giving a nice introduction. So let me share the presentation first. Can you see this?
Yes, ma'am.
Yes, ma'am.
Just 1 minute. Is it the full screen? Is it coming as full screen or not? No?
Yeah, full screen. It's coming off full screen.
No,
I think I need to, just 1 minute. I think I need to share the window instead of just sharing. Is it full screen?
Yes, ma'am.
Okay. I mean, can you see the slide full screen or?
Yes, ma'am. It's visible properly. I think it's okay.
Okay. So good evening to everyone. I'm really happy that I have been given a topic which is very close to my heart, because although I don't get much opportunity to work in the HPC world, because I had to work in other areas like Internet of Things or wireless sensor network, but still I love this particular area very much, which is high performance computing. So that's an opportunity which has been given to me by Taposhi and Kamalesh during designing this particular program. Okay, so I will go through these topics during the first part of my lecture. So let us start with an event which happened in the year 1996. So there was a match between the chess champion Gary Kasparov, and the IBM computer Deep Blue. Deep Blue was the supercomputer built by IBM at that time. So this match in the 1996, you can see a picture of Deep Blue on the right hand side. So this match in the year 1996, in this match, actually Kasparov won. I hope you I mean, many of you might not have born that during in the year of 1996, but I hope you have learned the name of Garry Kasparov, who was chess champion at that time. So Kasparov and Deep Blue played the game chess, and Kasparov won. But then the scientists of IBM, they made some changes in the supercomputer Deep Blue. And in the year 1997, a rematch was organized. And in this rematch, you can see the result. The first game was won by Kasparov. The second game was won by Deep Blue. Next three games were drawn. And then in the sixth game, Deep Blue won. So Deep Blue defeated the champion, the then champion, Garry Kasparov, chess champion, Garry Kasparov. So I have written that the match that changed history. Why? Because now all of us are talking about artificial intelligence. But just before start of this millennium, this particular event changed the history, because during the 80s and 90s, no one was talking about artificial intelligence. And actually, we call it artificial intelligence winter, because the funding was very poor. No one was talking about artificial intelligence. But this particular event changed the history. And again, we started talking about artificial intelligence. And then machine learning came, and then several things happened. Cloud computing, obviously, the technology which is enabling all these things. But we need to remember this particular event, because after this particular event, the public actually started giving importance to high performance computing. Before that, high performance computing was only known by the scientists. But this is the first time after this event, public started talking about high performance computing. So how was Deep Blue? Deep Blue, I have given the configuration here very briefly. 30 processors and 480 single chip chase search engines. These cheap chase search engines, single chip chase search engines, these were developed by IBM. And these chips were configured in such a way that the chase search engine could be embedded into the chips very easily. Right, and those those processors and these search engine, these chips could perform a set of coordinated high-speed computations in parallel. Each node was RS6000 SP computer with 16 chase chip on each processor, right? 1 GB RAM and 4 GB disk. So the nodes could communicate with each other using high-speed switch. The operating system was AIX 4.2, IBM's own operating system. During that time, Linux was not popular at all. And the processing speed achieved by this particular computer was 11.38 billion floating point operations per second, or 11.38 gigaflops. I hope you know about the flops, floating point operation per second. We use this metric to measure the performance of the supercomputers. This chase chip was capable of searching 2 to 2.5 million chase positions per second. You know the search algorithms of AI, artificial intelligence. So this was able to so many chase positions. Deep Blue was able to evaluate 200 million chase positions. If we consider all these and 480 single chip chase search engines, then we will get 200 million chase positions per second. And I hope you understand why it could defeat Kasparov, although surely we should salute Kasparov, that Kasparov could defeat Deep Blue more than once. So how was HPC evolved? We need to understand, because we need to go through the evolution of HPC before coming to cloud computing. So initially, We can start with Cray 1 because that was the first, in some way that we can say that that was the first parallel computer which was built in 1975 by the Cray company. It was just a vector processor. What do we mean by vector processor? Vector processor means it can take any vector as input, perform more than one vectors as input, and perform some operations on those vectors, and finally output the results. So basically, if you remember Flint's taxonomy, this is a single instruction, multiple data sort of computer. And earlier, most of the parallel programming which were tried by the scientists or parallel programmers were actually such type of vector processing, like it could be vector addition, vector multiplication, etc. And the other configurations are given here. I just wanted to highlight even this vector processor, which could run only very few programs, which are embarrassingly parallel. So only this very few programs, for running very few programs, this vector processor could use 20-ton compressor for freon cooling system. So freon is one type of gas which is used for cooling. So 20-ton compressor was used by this particular machine. Then in 1980s, more parallel computers were developed, built by different companies. I just highlighted two more from Cray company. One is again two vector processors. So now the manufacturers, they started, instead of just a single vector processors, they started harnessing more than one processors, vector processors. Vector processors are not like microprocessors. I hope you understood by now. So they started using more than one such processors in one single machine. Like in the next one, they have used 2, 4, or 8 vector processors, and the flops were also increasing. That means this particular machine, Cray XMP, could execute 200 megaflops per second, and this one 333 megaflops per second. But in both cases, in fact, the design was such that the memory was shared. So all processors could share the same memory. So if the data is not different, not multiple, not different, then obviously some kind of synchronization was required. But vector processors were unable to do any kind of synchronization for the concurrent access. Okay. So 1970s to 80s, in addition to vector processors, we found another type of machines were being built. One of the major manufacturer was SGI, Silicon Graphics. Okay, so they started building shared memory multiprocessing systems. These shared memory multiprocessing systems again could use 8 number of processors with access to the same memory space, then again shared memory, and inter-process communication took place via the shared memory only. But the scalability of such kind of shared memory multiprocessors was very poor. As I mentioned, we could only use maximum 8 processors. Beyond 8 processors, it was practically impossible to work with, because the processors would automatically become, because of high memory access, the speed of the parallel programs would become very poor. So scalability issue was there. So scientists were thinking, can we move to something different type of systems? So there were many such attempts. It's not possible for me to discuss all those attempts, and that's not the topic also for today. I'm just very briefly trying to say the history to understand why we have come to the present world. So in 1985, Intel started building another kind of machine. Here actually independent processors, each with some memory, were connected in the form of hypercube. So you can see the picture here. So the processors Intel used are very generic type of processors, because that time microprocessors were already invented, and many we know the PCs have come up during 1985. So 80286 processor, very generic type of microprocessor, along with 80287 math processor, were used as one single node of this hypercube with 512K RAM. And there were certain Ethernet ports, because we need to connect this in the form of hypercube, and a message, and on top of this hypercube structure, a message passing interface was used for programming, which was called NX. Now, many of you must have heard about MPI, message passing interface, which has become a de facto standard for parallel programming on top of some type of machines. We will talk about that later. So, but here during the 1980s, there was no message passing interface, so NX was used for programming such type of parallel computers. In 1994, Beowulf cluster was built. I just quoted one line. Beowulf is a very old English poem. Okay, and in the poem there is a line. It has been translated to modern English. Because my heart is pure, I have the strength of 1,000 men. So Beowulf, the cluster which was built by the scientists, gained the strength of 1,000, maybe 1,000 processors or whatever you say. So actually, when Donald Baker and Tom Sterling, they worked in at NASA, they built Beowulf cluster. They named it like this, where all the available PCs were interconnected using the network, which was commonly known at that time, and now also we know that Ethernet. So that time it was 10 megabit per second Ethernet. So 16 Intel, in the first machine, 16 Intel 486DX PCs were connected using the Ethernet, and it could achieve only 1 gigaflop per second. So Beowulf cluster actually, again, it changed the history in the sense that instead of building supercomputers in the factories, which are not which are built with special kind of hardware, software, we moved to an era when we could actually use the commodity hardware and the normal operating systems like Linux for working with high-end computing, or rather high performance computing. Parallel programming was possible during that time. So I highlighted this particular event again because that paved the way of the newer computing infrastructure, which we call, which we know as grid computing, cloud computing, etc. So unless these two persons never thought of clusters, we could probably not appear in today's modern world for cloud computing. 2000, in the beginning of this century, hybrid clusters were built, because now see, hope you heard about Moore's law. Moore said that the clock speed of processors would will be doubled during every 18 months, within every 18 months, and we will be, the number of transistors which we could place on a chip will be doubled in every 18 months. So Always we actually thought, when probably I was also doing my research in the University of Manchester, we were talking about there is a physical limit. So how is it possible that this processor speed and number of transistors we are placing on a chip will be increasing again and again? So how is it possible? So we need to invent something else. We need to think about different type of parallel programming. So all these things we were thinking in the 1990s. In 200, again, another invention was made by the chip manufacturers. So instead of increasing processor speeds, they started increase the number of processor cores. So on the right hand side, you can see we have 8 nodes which are connected through a network. Okay, and each node again have 2 CPUs. Each CPU is actually divided into 4 cores, right? And this 4 core, that means a quad core processor. Now we call it a quad core processor. So in 2000, before 2000, this was not known. This technology was not known to us. So quad core processors, and there is a bank of memory which can be accessed by these quad core processors. So hybrid clusters were built with a large number of processors, each with a small number of core, sharing RAM and some cache space. So now we know when we talk about such type of nodes, we have processor cores. On the processor cores, on the chip, we have level 1 cache. So actually we are using different levels of caches. So we have level 1 cache, which is exclusively accessed by one processor. Then level 2 cache, which is maybe shared by uh, mm, uh, more than one processor. So this way actually we have levels of caches, and also we have shared memory. So a particular node can now access the shared memory, as well as they can access the data on their own cache. So the entire design of the chip was changed through this type of changes in the technology. Okay. So today's top supercomputers, because we always talk about the supercomputers. So today's top supercomputers are hybrid clusters, which have a large number of standard processor nodes. And each node is a multi-core processor with individual cache, with shared cache and RAM shared by all cores. And also there are GPUs in the clusters. Now we are using GPUs or other accelerators which are used for offloading specific type of computations from the CPU nodes. So GPUs, when we talk about, actually there was some discussion about whether we go for data parallelism or task parallelism. By data parallelism, you understand, based on Flint's taxonomy, we talk about single instruction, multiple data. But when we talk about task parallelism, then this is a MIMD kind of programming, multiple instruction, multiple data. So when we use GPU, so when we started parallel programming on CPUs in the 1990s, we started a hybrid a mixture of task parallelism and data parallelism. So even the programming paradigms which were supported at that time supported both task parallelism as well as data parallelism. But when we talk about GPUs, then basically GPUs are accelerators which are mostly I mean actually supports data parallelism. So now it has become possible in the CPU we will apply some task parallelism, and tasks are again offloaded onto GPU so that some form of data parallelism can be can be made possible. So this was this type of programming techniques evolved during the first decade of 2000, and now also we are using this type of programming. So computation speed, however, always often limited by data movement rate. So this shows the evolution of HPC starting from so this side is big iron, that means single big machines which are occupying almost one floor of a building, large building. And we also have decentralized collections in this way, this side. So you can see how how it changed. Centralized computer, then decentralized collections, then again centralized computers, then again clusters, etc., grids, etc. The HPC machines evolved in this way. This shows a screenshot of top 500 supercomputers, which I collected from the top 500 website. This list was published in November 2024, and you can see the first one is in fact, many of them are in United States. Only the fifth one is in Italy. So they are using 11 how many 11 1 crore probably cores. Okay, this one also very large number of cores. All these are using large number of cores. The other configurations are also there, but I did not include other configurations. Some configurations are given here, like AMD chip. This is also we have Xeon. This is Xeon Intel CPU. So the configurations are given here. If you go to top 500 site, you will be able to find this particular list. The logical organization also changed over the time. So we started with this type of logical organization. We have the processing elements, all the processing elements, and there is a global control unit, a kind of vector processor, and the interconnection network is connecting the processing elements. So obviously there will be shared memory. In this case, the control mechanism is distributed. So the processing elements are having their own control units. So this is for single instruction, multiple data, and this is for multiple instruction, multiple data. More clearly, it is shown in this diagram. Here we have shared memory and the processors, and we have the interconnection network. This type of logical organization is called uniform memory access shared address space computer, because the memory is shared, so shared address space. And because the processors will take same amount of time to access any of the memory locations on this side, so it is uniform memory access. In this case, again, we have same uniform memory access shared address space, but each processor has some amount of cache on the particular node. But this is completely different. The logical organization is different, because here each processor has its own cache as well as memory. So if a particular, and the physical organization will also be similar to this one, because memory is now on the same node where the processor is lying. So therefore, each processor will be able to access its own memory very fast, but when it will access the remote memory, that will take more time. So that is why it is called non-uniform memory access shared address space computer. And here actually, this has become very common type of hardware nowadays. As I said, we have CPUs with multiple cores. The controller is here. We have the memory shared by these CPUs, and this forms one particular node. And we can have many such nodes, which are interconnected through a interconnected through a fast network, and that will form a cluster. So such type of shared memory nodes can be programmed using OpenMP. OpenMP is a shared memory programming model where we will send the instruction, like if it is a loop, we will be able to run multiple portions of the loop on different processing units at the same time. So OpenMP or pthreads and even MPI will also run on this type of nodes. But when we connect through a cluster, we can use MPI, message passing interface programming language programming. I mean, it's a there are compiler directives, the libraries, etc., which will enable us to run a program parallelly on different nodes. So this becomes a distributed memory machine, whereas in this case a shared memory machine. And there are other variations which I don't have time to discuss now. Rather, I will, if you have any questions.
Can I?
Yeah, sure. Well,
In
yes.
Between HCI computing and cloud computing. Cloud
Sorry.
computing. HPC and
No, I didn't start discussing cloud yet. I'm coming to that. Just okay. Is it okay? Shall I carry on?
voice is not clear.
Okay, let me.
Ma'am, you
Right.
can continue. Ma'am, you can continue.
Huh?
You may continue, ma'am.
Okay. So now these are some of the pictures of the largest supercomputers which are located in different geographical locations of the world. Like this is from Jülich. Jülich is in Germany. You can see that the so many machines. This is one single supercomputer, Blue Gene, IBM, from IBM again. We got this picture in 2013. I just wanted to show these pictures because if you see the say the setups, the whatever we have here, see these are the cooling system. So in this case also you will find some pipes overhead which are cooling systems, which are I mean almost $6 million argon gas is flowing through these pipes to make it cool. And similarly here again we have some cooling system, electrical systems underground. So maybe a 3-storied or 4-storied buildings are being used for housing such type of computers, supercomputers. The major problem is when any organization purchases any supercomputer, the question is what size on-premise system should we buy? That's the main question. Because with respect to system utilization, if you see this, this is a graph over time showing the system utilization. Now, in most of the time, these are the peak loads during this time. So the system can handle the peak load, but most of the time the system remains underutilized. This is one of the major problem of high performance computing, which we have seen till maybe 2010, 12, something like that. Because the system cannot be, if a particular organization owns one such system, the system cannot be used for the entire time up to its peak load. That's not possible. That can never be possible. And there is no history that the system has been utilized up to the peak load for a very long time. So this is one problem which was the even the organizations who owned the supercomputers, the governments, all of them started thinking what to do with this. And for us, who worked in some institutions where there is no funding to buy any such computers. In fact, any such computers could not be bought by any of our organizations in India. So that was not possible. Large supercomputers, that was never be possible. Such supercomputers which can be placed in among the top 500 supercomputers, it was never be possible. So therefore, although CDAC made some attempt, but as you understand, there's such a huge cost, not just procurement cost, the maintenance cost is also very huge. So therefore, it would never be possible by a country like ours, by any organization in a country like ours, to purchase a supercomputer which will be able to do lot of high performance computing within a very little time. That's not possible. So scientists started thinking about something else. So what do they started thinking? We started with mainframe computer, then I talked about cluster computers, then in the although it started from 1990s, but actually it was on the top in sometime in 2004, 5, 6, like that, the type of computing which we called grid computing at that time. So what is grid computing? Grid computing, I'll come to the definition. I am coming to the definition, but just one sentence about grid computing. Grid computing tried to harness the power of many small computers, giving an image of one single machine to everyone, so to the users. So that was grid computing, whereas cloud computing is very different from grid computing. I will again come to the idea of cloud computing. So in case of cloud computing, we have large machines, and anyone who wants to use anything from the cloud will be able to take some portion of the resources and use for their own purpose. So this trend the changes happened during the last 40 years. So when we talk about grid, the definitions are here, but I would like to, so it is a flexible, secure, coordinated resource sharing among dynamic collections of individuals, institutions, and resources, or single seamless computational environment in which cycles, communication, and data are shared. Collection of geographically separated resources. So please note here, actually they talked about people, computers, instruments, data sets, everything. Everything was actually harnessed togetherly to give one single image of the machine. But one particular keyword I would like to highlight here. Grid started with the concept of sharing, shared. Whereas cloud said offers on-demand, scalable, and elastic computing and storage devices. The resources used for these services can be metered, and users are charged only for the resources used, right? So whenever I try to compare between grid and cloud, I always give examples like this. Grid is like, say, a number of poor persons who have little resources. They are trying to use their little resources in shared mode and thereby try to perform high-end computing jobs. Whereas cloud is like a rich person who has a huge resource, and this person will actually give the resources to other users as some kind of pay-per-use model as and when required. So they will give as a service. I will come to the service model later. So cloud computing models. So cloud, I mean, the with different companies. So cloud was actually built in the universities. Universities started building clouds, but universities were more inclined to build grid, particularly in United Kingdom, in USA. Different institutions built grid, but then when they proposed the cloud model, then many of the companies, IT companies, they picked up this model. And they picked up this model and they suggested, because by that time service oriented architecture was also here, so they suggested different delivery models. But before that, they used infrastructure which was a distributed infrastructure. They used the key technology, resource virtualization, and autonomous systems. Okay, so resources were used, not just computers, compute and storage servers, networks, applications, and other type of services. I'll talk about services later. The attributes, defining attributes, were massive infrastructure. As I said, cloud actually belongs to rich companies who could procure such type of massive infrastructure, as the pictures which I have shown earlier. Utility computing, pay per use model. So whenever you take anything, you just pay for that. Accessible via the internet. It should be accessible via the internet. And elasticity. Elasticity is the major requirement for a cloud to be to provide services to the users. So with this elasticity, I hope you understand. Yeah, elasticity means you can increase as much the resources as much as you want at a particular time, and then you can again decrease the resources whenever it is necessary. When you don't need more resources, you won't ask for resources. When you need more resources, you can increase those. So the delivery models which were proposed by these cloud builders or cloud providers were software as a service, platform as a service, and infrastructure as a service. And many of you perhaps have used cloud, so you understand that infrastructure as a service is provided by AWS, for example. Platform. I will come to all these service models in my next lecture. And deployment models were also public cloud, private cloud, community cloud, and hybrid cloud. We will talk about this. So cloud computing allowed virtualization of resources. So that it has become the basic enabler of cloud computing. So cloud computing simplifies management of physical resources for the three abstractions which I just talked about in my previous slide. So the state of virtual machine will run under a virtual machine monitor, or it is also called hypervisor. So anytime the state of virtual machine can be saved and migrated to another server to balance the load. That is one of the major requirement and also advantage of cloud. So in case of a normal high performance computer, if the computer is down, if some nodes are down, or if entirely the computer is not working for certain reasons, you will not be able to execute your job. Whereas in this case, your job can be migrated to another server, and even if it is if the server is overloaded, then also the job can be migrated to another server without users intervention. That is the major thing. In case of cloud, you don't need to worry about whatever is happening in the underlying hardware. It will be done by the virtual machine monitor, this hypervisor. Virtualization allows users to operate in environments they are familiar with. So if you are unaware of any of the operating system like IBM operating system, you can always work with Linux. You can ask request for Linux operating system from the cloud provider. So you don't need to be forced. You are not being forced to use specific type of hardware and software resources. So therefore, virtualization, as I said, that is the enabler. We have the physical machine, we have the virtual machine monitor here, and accordingly, if the users ask, say 3 clients asked for, here we have 4 processors and 8 GB memory. 3 users ask, clients ask for 1 CPU, 3 GB memory, 2 CPU, 1 GB memory, and 1 CPU, 4 GB memory. Then this virtual machine monitor will virtualize the physical machine, prepare these 3 virtual machines, and provide the clients so that the clients can use according to their requirements. If at particular point of time the first client need 2 CPUs and maybe 3 GB more memory, that can also be given by the virtual machine monitor, taking from this physical machine. If that is not possible from this physical machine, that can be obtained from some other server. Okay, so this is, or the entire virtual machine, this virtual machine can actually be migrated to another server and enhanced with the new CPU as well as memory blocks. Okay, so that is the advantage of virtualization. So virtual machine monitor hypervisor partitions the resources of computer system into one or more virtual machine, as I already said. It allows several operating systems to run concurrently on a single hardware platform. So you can have multiple services to share the same platform, as we have seen in the earlier slide. Live migration, I already mentioned. System modification while maintaining backward compatibility with the original system. If a new operating system needs to be loaded, that can be done with backward compatibility, and enforces isolation among the systems. So these 3 systems, 3 virtual machines are isolated from each other, therefore ensuring security among them. So virtual machine is an isolated environment that appears to be a whole computer, but actually only has access to a portion of computer resources. So this VMM can, one such VMM can trap the privileged instructions exist. So actually we have that, now we have the concept of host OS and the guest OS. Host OS is the operating system installed on this particular machine, whereas a guest OS can be installed on any of these machines according to the user's requirement. So whenever a guest OS raises a privileged instruction, that can be trapped by the virtual machine monitor, and it will enforce the correctness and safety of the operation by forwarding to the host OS and making it executable by the host OS, so that correctness is enforced. Similarly, traps from outside the it interrupts from outside and dispatches them to the individual guest operating systems, so that the guest operating system can actually execute the whatever is asked by the interrupt. Okay, VMM obviously controls the virtual memory management, because now these memory blocks are shared among the different virtual machines. So memory management will have to be done by the VMM. It maintains a shadow page table for each guest OS and replicates any modification made by the guest OS in its own shadow page table. This shadow page table, that means the hypervisor's shadow page table, points to the actual page frame, and it is used for memory management unit for dynamic address translation. So whenever any memory is accessed by the guest OS, by the applications on a virtual machine, that will be translated accordingly by the virtual memory machine monitor or hypervisor, and will be sent to the memory management from memory management unit to the actual memory block. It also monitors the system performance and takes corrective actions to avoid performance degradation. So there is one example, like when there is a lot of thrashing, then VMM may actually swap out a VM. It may send the VM to somewhere else, or it may send warnings to the user, or it may take some decisions accordingly. So this type of hypervisors, basically they are now the lifeline of the virtual machines. In fact, we have heard about virtual machines when Java, when we started programming with Java. So whatever I am not going back to that discussion, but whenever we have the VMMs or hypervisors now, we actually can use two types. Like here we have, in the first type, we have the hardware. The hypervisor is located just above the hardware, and therefore it is called bare metal or native. So on top of this hypervisor, the virtual machines are created with guest and the applications are running on top of guest OS. On the other hand, in type 2, so VMware, Zane, VMware is ESX, Zane, these are the example of this type of bare metal hypervisor. On the other hand, in case of second one, the type 2 hypervisor, we have the hardware. On top of that, we have host OS, and VMM or hypervisor is deployed on top of host OS. And again, on top of hypervisor, we have these VMs with guest OS and applications running on the VMs. So these are the basic models of cloud deployment in with hypervisors. I have given a list of list of some hypervisors, example of hypervisors, like integrity VM provided by HP, where host OS can be HP Unix, guest OS can be Linux, Windows, HP Unix, etc. There is an ISA, some ISA supported by these VMs. So here actually x86-64 is supported by this one. Similarly, we have several others: Power VM, Linux Secure, Oracle VM. We mostly use VMware. Again, we use Zane, for example, which supports x86 ISA, and Linux Solaris as host OS, Linux Solaris NetBSD as guest OS. The providers' names are also given here. This, as you can see, Zane was developed by University of Cambridge, whereas Denali was developed by University of Washington, and others were developed by the companies. Okay, so some of the hypervisors we can use for setting up our own cloud as well. So gradually, when it was started in the years 2007, 2008, gradually the takers of cloud increased very fast. So you can see this particular uh, graph where it was almost, I think it was almost have become maybe 5 times or so, at least 4 times within a few years. Starting from 2017, we moved up to 2025, and the users increased. Sorry, 2024. The number of users increased so rapidly. So this is one picture because, as I said, the instead of setting up our own infrastructure in our premises, most of the uh, institutions, most of the companies, most of the businesses, they are now moving towards cloud, because now they will be able to uh, run their own applications, own programs on the cloud, which is just provided by somebody else, some other company, who and we don't need to pay, we don't have any initial infrastructural cost, and we don't have any maintenance cost. We only need to pay whatever we use. So it is a pay-per-use model. uh, Such type of concept is now being adopted by most of the institutions and most of the companies. In fact, our researchers also now they are also using different type of cloud-based applications like Colab, etc. Okay, so many of you probably have used Colab already. Um, so this is something, some changes in the uh, technology world which are affecting all our works. So what is the new trend in high performance computing? Along with um, cloud computing, we have also witnessed a rise of big data, right? Big data, the amount of big data. Perhaps you are already aware of big data with the 5 V's, the properties: variety, veracity, volume, velocity, etc. So I'm not talking about that. But what is happening? Our daily interaction on mobile, particularly from the public, social media, and the Internet of Things, are creating more data than at any point in our history. So 90% of the data in the world was generated in the past 2 years. Also, AI, I started with artificial intelligence. Artificial intelligence uh, has become the most, everyone is talking about artificial intelligence, the most uh, used buzzword or popular buzzword now. And massive data processing tools are available, complex machine learning algorithms are available. Uh, we need increased computing capacity to train larger and more complex models faster. Therefore, this artificial intelligence and big data enabled us to develop or to apply the algorithms in much newer domains, which we never thought about in the early days of high performance computing, right? So most of the companies who are offering data science services now moving to cloud, because they don't need to worry about physical hardware. Version management is one important work for the tools, but version management is automatically done by the cloud-based tools. Even for the applications, your applications you have deployed on the cloud, but the version management will be done by the cloud. So instead of maintaining a monolithic cluster, which we knew earlier, uh, so this cluster, monolithic cluster like Bayes cluster, could support many workloads. Say you are writing a financial application, you are writing a molecular dynamics simulation, everything you could run on the same cluster. But now, instead of using the same cluster high performance computing for high performance computing of different types of workloads, now you can create many small short-lived clusters which are designed to run specific jobs. Specific jobs can be run on this type of short-lived clusters. So data is now stored in cloud storage. Cloud storage is also provided to the users separately. So you can store your data on the cloud storage to support multiple temporary processing clusters. You don't need to install no need to install the infrastructure along with storage in your premises. No need to use the same type of machines for different types of workloads. So again, whatever we need, we can ask, demand, or reserve from the cloud, and then accordingly we can work with such type of cloud. Yes, sorry.
দাদা ক্যারি ব্যাগটা নিন দেখি ও
So this type of clusters are often called as ephemeral model. Ephemeral models are used for processing jobs which are allocated as needed and are released as jobs finish. So this is a new thing which we never knew for high performance computing, and that is why I talked about the history so much time, because unless we know the history, we won't be able to understand what are the advantages of cloud for our own purpose. So the user only pays for what resources are used, that I mentioned several times. So the thing is, now you have your own, you have written a program for some purposes. Whatever resources are required by the program, just ask for those resources from the cloud, deploy your program there, run your program, store the data on the cloud again, and again release the resources. You can keep the storage resources because you may need to go back to the data several times. So if you need the data, you keep the storage resources, but the other resources can be released whenever you need. So actually, this is a pay per use model, where whatever resources you need, you acquire the resources and release when you don't need. So you don't need to think much about the hardware procurement and maintenance. Here is an example of Google Cloud. Google Cloud includes a data proc a tool, which is, I'm not sure whether it is visible to all of you or not. I hope it is visible. Google Cloud includes data proc. Actually, this is a normal data center without cloud, where you need HDFS disk-based cluster 1 and cluster 2. On top of HDFS clusters, we have 4 jobs. 2 jobs are running here, cluster 2, and 2 jobs are running on cluster 1, right? So instead of doing this, we can actually migrate the entire system to the Google Cloud platform, because in Google Cloud platform, we have buckets, storage buckets, where we can have single bucket or multiple buckets. This is part of cloud storage. Our data can be, instead of HDFS separately here, our data can be stored in the buckets, and the jobs can be migrated for running on different clusters. So as you can see, instead of having just 2 HDFS clusters, here we have created 3 clusters. On one cluster, job 1 and 2 are running, and job 3 is running on cluster 2, job 4 is running on cluster 3. So Dataproc will provide such type of environment for any kind of high performance computing usage. When I talked about HDFS, I hope you understood that I'm talking about a big data tool, Hadoop, which applies map-reduce programming on top of a storage like HDFS. So MapReduce programming will run parallelly on the Hadoop nodes and get the results using mapping map and reduce. So that is something which is happening here, and that it is also possible to port to the Google Cloud and creating the clusters whenever we need according to our requirement. The clusters are also created according to our requirement. Say, for example, for a data intensive job, we need more memory, but less number of CPUs. So we can use maybe say some CPUs, small number of CPUs, say n number of CPUs and k gigabytes of memory, where k is much larger than n. Whereas in case of, so this is for a data intensive job like financial management. Whereas in case of molecular dynamics program, the data may not be much, data may be less, whereas we need more processors because we have complex computations. So in those cases, we would need, say, n number of processors and kgb memory, where n is much more larger than k. So this way, actually, we can decide what type of clusters we need. So HPC on cloud, what are the advantages? Obviously, I mentioned most of the advantages, but I again repeat the availability. Even if the actual physical machine on where my job is running presently is down or crashed, then also we can migrate to some other physical machine. That support will be given by the cloud provider. For obviously cost effectiveness, because I don't have the procurement and maintenance cost, I am just paying for the resources I am using. Elasticity is there. Whenever I need more processor, more memory, or more amount of resources, we can go for the more resources, and we can release the resources whenever not required. Isolation, I already discussed. So demand of HPC is increasing among business and companies worldwide for information and operations like fraud detection. We never thought about such type of applications on normal high performance computing machines, like fraud detection, because now a lot of data are being generated on the internet. So companies are looking for programs which will enable such type of things like risk analysis, which so risk analysis is dependent on huge amount of data, maybe for financial management. So companies are now trying to analyze the data and then get some prediction about risks, which can only be done on uh, high performance computers. But there is no need to buy high performance computing machine at this moment. We can go for cloud and we can run these algorithms. There is one more technology which is actually supporting such kind of movement from uh, regular use from normal high performance computing machines at the data centers to cloud based high performance computing machines, that is called RDMA, or remote direct memory access. So high performance RDMA instances such as virtual interface architecture and InfiniBand, these are the two RDMA instances, two providers of RDMA instances. They are more or less making cloud computing possible as we know it today. What is this RDMA? It is the ability of multiple computers to share data with one another without affecting each other's processes. So you have you have some data stored on the cloud storage, and using RDMA networking, there may be multiple virtual machines used by different users, uh, who can share this data and without affecting others' process. This was not possible when we had the normal, or whenever we use the normal high performance computing machines. This is possible on cloud. So many advantages are there. This particular diagram on the left hand side shows us a normal HPC environment in any data center, where we have high speed interconnects at the bottom, MIDINET, etc. On top of that, we have parallel computing hardware. I have spoken about parallel computing hardware. On top of that, we have third party, because there cannot be any fault tolerance. So either we have no fault tolerance or a third party fault tolerance. Um, on top of that, the programming interfaces, libraries, etc., message passing interfaces, parallel Fortran, high performance Fortran, actually high performance C++. These are high performance languages for parallel computing. And on top of that, we have computationally intensive models. I'm sorry for this spelling mistake of variable, but I took the image from somewhere else, therefore the mistake is still there. I didn't notice it earlier. So variable size data and task dependency. So again, we have HPC applications running on top of this. So this entire part for normal data center is managed by the HPC middleware and HPC hardware manages this part. Okay, so the cost is very high, availability is poor. Language platform, we have old high performance Fortran, C, etc. Fault tolerance, as I said, it's third party fault tolerance, and reliability is high. Obviously, you have your own machine, so always that is very much reliable. So that thing is there. So it's reliable, but in the other aspects, we do not get what we actually want. On the other hand, when we move to cloud, where we have uh, hardware, hardware located in different geographical locations, this may be high-end servers or may not be so much high-end servers, but their power can be harnessed together for parallel computing. So we have parallel computing commodity hardware here, uh, fast interconnect, gigabit interconnect connecting these machines. We have Hadoop, actually Hadoop fault tolerance or any other fault tolerance can be used here. These are just example of Hadoop running big data analysis on top of cloud. Big data map reduce tools, solutions can be run here, and we have data intensive models, large size of data, independent tasks. On top of that, we have the applications. Here you see reliability is poor because the hardware is not maintained by you. So the infrastructure and platform may be managed by the cloud providers. Whereas fault tolerance is there, language platform is there, accessibility is there, availability is there, and cost is also very low. So these are the advantages of cloud platforms, and I mentioned advantage and one advantage and many disadvantages of normal HPC platforms at the data centers. So if we merge these two, then what we can get is this one. So we have the commodity hardwares uh, located in different geographical locations. We have the high speed in the data centers. We have the high speed interconnections, or we can have fast internet, gigabit internet. We can use Hadoop fault tolerance here, and we can run the message passing interface, etc., on top of these tools. And on the other side, right hand side, the map reduce programming. And we can have the same environment as an HPC uh, computer we used in the data centers, and the same another environment can be created for our data intensive HPC applications. So on this side we have compute intensive HPC applications, on this side we have data intensive HPC applications. So if we port this HPC towards the cloud, then we now have we have low cost, because as I said several times, pay-per-use model. We have the availability, high availability, because anytime we can migrate. We also have the languages on this side, our known languages, MPI, OpenMP, high performance Fortran, etc., because that type of libraries can be deployed on top of as platform on top of the host OS and guest OS. Okay, and we can have fault tolerance using some tools providing the fault tolerance. We also have reliability using such type of platforms. Okay, so this is something which is happening now. The entire business is being ported to and the high performance computing solutions are being ported to the cloud. So this is a newer trend in HPC arena. So obviously there are some HPC centers in different places in the world. I will come to that. But before that, we should talk about the new wave in cloud, which is the services of GPUs. So many now the cloud providers are integrating GPUs with their cloud platforms, because earlier we used GPUs, and now also we use GPUs on our own laptops, or maybe on the servers, or maybe on the workstations. We have our own GPU programming, GPU programs running on our own machines. So that is still possible, but such type of small GPUs cannot satisfy the requirements which we are facing nowadays for huge amount of data we are using for machine learning or training the artificial neural network or other machine learning models. Okay, so therefore cloud platform providers are now offering on-demand GPUs. So GPU cloud, we will get GPU cloud nowadays as public cloud. So that will come as infrastructure as a service. I will come to these concepts a little later in the second lecture, during the second lecture. So this GPU public cloud provides computing resources such as RAM, storage, CPUs, as we have used earlier, but along with that, graphics cores, GPUs as well. So this type of usage of GPU cores help us to address tasks which would require enhanced computing power. I talked about data parallelism. So now massive data parallel tasks can also be deployed on cloud, where we can use GPUs for satisfying our requirement. So a graphics core can perform 10 to 14 times more operations than processing cores. So with all these details, now I would like to call it democratization of HPC. Why? Because HPC was owned by only some of the organizations who had high performance computing machines, or rather supercomputers, in their premises, like ULISH, like San Diego, like Argonne National Laboratory, like so many in large institutions and organizations. But because of cloud computing, now for the public, HPC access has become possible. So it's not only for traditional users. non-traditional HPC users can also um, access parallel computing or do high performance computing with cloud. Like Amazon Web Services, Microsoft Azure can provide actually provide HPC friendly public cloud for solving many HPC problems. You can use these services. Non-traditional HPC users like business people, they are now worried about the risk analysis of their or financial management, so they are also leveraging public cloud HPC solutions. So now companies are coming up who will use public cloud infrastructure for high performance computing solutions and provide solutions in non-traditional fields like financial management. So they, and also this can be used to solve machine learning and artificial intelligence challenges. With big data applications, opportunity for exploiting data parallelism increased. I talked about data parallelism. We have huge data. We can train artificial neural network models using cloud, HPC on cloud. See, now whatever um, good machine learning models are being trained, those are being trained on HPC cloud computing. Without the support for HPC, it would never be possible to train such type of large machine learning models. I have seen the schedule, so there are other resource persons who will be talking on these topics. Rise in GPU computing. Also, I mentioned because of GPU computing in high performance parallel computing using data parallelism, massive data parallelism has become possible. In 2019 itself, top 500 supercomputer ranking list includes 136 NVIDIA GPU accelerated supercomputers. So supercomputers are now relying on GPU accelerated supercomputers, so GPUs. Artificial intelligence goes mainstream. I have already mentioned that from the data center to the edge computing. Now we are also moving when we are when we are working with Internet of Things or other domains, we are actually moving from the data center, uh, centralized cloud platform to the edge for service delivery, for caching, for computing offload, and for IoT management. So cloud is not alone now. Cloud has actually now become associated with edge computing for solving several new upcoming uh, technologies, including Internet of Things, including say different other like Internet of anything, then cyber physical, many types of cyber physical systems. So everything, new technologies are coming up all over the world. So this is a quotation from a paper which Jeffrey Napper and Paolo Biantinesi published in 2009. They said the title of the paper was "Can Cloud Computing Reach the Top 500?" That means, can cloud computing will ever be able to address the requirements of high performance computing? The quote is, "It appears that regardless of how many nodes are used, a cluster built out of current EC2 nodes cannot attain a spot on the top 500 list." Which means they said that cloud computing will never be able to deliver, at least at that time they said, will not be able to deliver the requirements for high performance computing. So I will go back to the list which I have shown to you earlier, top 500 supercomputer list. Here we have only included top 5, and among the top 5, Eagle is a uh, machine which is based on Xeon Platinum machine, uh, and Eagle deploys Microsoft Azure Cloud. So basically, it is a cloud HPC provider. And so 20 lakh crores, sorry, 20 lakh, almost 20 lakh cores are used by this type of machine. Okay, so you can see, and obviously if you go through the top 500 list, you will find many more such type of cloud platforms which are which could be included among the top 500 supercomputers. So that's a huge change, massive change. Starting from cloud was we started working with cloud. I mean, the world started working with cloud in the year 2007. In the year 2009, Amazon was providing EC2 cloud services, cloud services, and gradually that time we could never think that okay, cloud computing can go for HPC. We thought okay, cloud computing will only provide solutions to the small businesses or developers who are casual developers or maybe just app developers. But then suddenly everything changed within these how many years, maybe 16 17 years, everything changed. And now cloud, the entire HPC world is now moving towards the cloud computing. So that's a change. But still, can the entire HPC world will move to cloud computing? There is a question. Is it possible to fine tune the parallel code? Because you see, when we talk about performance of a parallel program, don't just, or when we execute a parallel program, which should increase the performance, the speed up should increase like this with number of nodes linearly. We don't get that in our real life scenario. We get something like this because there are overheads which are cost of starting a thread or process, cost of communicating shared data, cost of synchronizing, extra computation, load imbalance. So there are so many cache locality, etc. And the parallel programmers, they are struggling to reduce the overheads to get good performance for the parallel programs. Such type of fine tuning is not possible when we use cloud, because on the cloud you have no control over the resources, hardware resources. You can only fine tune your programs, but you do not know what is the actual configuration of the physical machine where your virtual machine has been deployed. So that's one this is one problem. So whenever the requirement if for parallel programs is very high efficiency, then I'm not sure whether cloud will be able to fulfill that type of requirements. So this is a question till date. I'm not sure. Maybe within few years there will be progress for fine tuning or for doing something. There will be tools, more tools. Now, whatever tools we get for fine tuning the parallel programs are all based on traditional systems, not cloud-based systems, like even fine tuning for GPU programs, etc. So, what is going to be within next 10, 12 years? We don't have any idea, but obviously we all expect that high performance computing on top of cloud environment should actually get lot of attention from the users and also should be able to fulfill the requirements of most of the users. With this, I would like to conclude the first part of the lecture with the conclusion. HPC is now evolving around cloud. It is now possible for non-traditional HPC users to work with HPC on cloud platform. Exponential growth has been seen for big data, and that made it possible to explore various new application domains by harnessing the power of AI algorithms and HPC on cloud. Okay, thank you for listening. So I think, shall we go for break, or someone was asking that?
Yes, yes.
Someone was asking about HPC or cloud. So I tried. This was the topic of the lecture. I think it was. You didn't notice the topic. So how HPC
No,
was?
actually, madam, what thing you are doing? You are just mixing high performance computing and cloud computing. But whatever you know, that cloud computing is in just it can use high performance computing, but parallel programming languages are these all these things are in cloud computing. Actually, whatever we know in cloud computing, that if we have some application and we want to run in a particular place, suppose the servers are not sufficient, then cloud computing provides some single click elasticity. Means single click you can extend, if whatever if there are millions of requests are there, then it will be accommodating that kinds of request.
No,
But
that
here
knowledge about cloud is not correct, because in fact, again in the next lecture I will explain some of the things, because when you use cloud, it's not just the not just the application you are using. Okay, because we will talk about different service models, where you will see that different kind of service models we can deploy on cloud, on top of cloud, so that you can use the parallel programming uh, parallel programming libraries like MPI, or uh, OpenMP, or even CUDA. CUDA also can be executed on top of cloud, because such type of facilities are now being given by many of the cloud computing cloud service providers. Does that answer to your question?
And cloud is
Yes.
also something, whatever I'm saying, that it is not costly, but it is costly, I think.
It is
If you
costly.
know your
No,
load, if you know your load, then I think the number of buying a particular number of servers and launching the application, it will be, I think, less costly. Because if you see whatever cloud providers, AWS, Google Cloud, as you know, if you see their cost, I think that will be taking much higher cost.
now you
If
will
the
have to
load is, I
compare.
think,
You will have to compare with the cost, uh, which will be you will have to spend if you buy a high performance computing machine. See, I was talking with one of my student few days back. I'm not my student, actually. Our research scholar, our departmental research scholar, is not my student. He is doing speech recognition in Indian languages. So he was telling me, I was asking what is he doing, etc. What is he is doing? So he was telling me, because he has a laptop with a GPU, uh, with a GPU, but whatever he wants to do, the complex program which he wants to run on this laptop, for such type of speech recognition, cannot run on his own laptop, because the GPU, although he has a GPU, maybe a very small GPU with say 1 GB memory or something like that, it cannot be run and run on on a small GPU. But if we want to buy large GPU or servers with large GPU, in that case, the cost of procurement, maintenance will be very high. So in comparison with that, cloud will give you resources at very low cost. Obviously, I'm not saying it is an ideal model, because I always preferred grid over cloud, but it's not possible. The business sectors were not interested for grid. But I'm not going into the debate now. But uh, if you compare the cost of a server which will be able to fulfill the requirement for, say, generative AI now, or other type of artificial intelligence or machine learning algorithms, obviously it will be very, very high. Maybe even a server of, say, maybe 24 lakhs or so uh, will not be capable to fulfill the requirements of such type of research. So for that reason, I am saying that if the users need high performance computing, truly what we call high performance computing, then for the users, normal users, it is not possible to procure very expensive machines. If you get the opportunity to work in San Diego, like Shubhashish will talk about San Diego supercomputing center, maybe he has a talk, right? So he will be talking about San Diego Supercomputing Center. In fact, I have shown one picture from San Diego Supercomputing Center. So if someone gets an opportunity to work there, if someone gets an opportunity to work with uh, some supercomputers installed in other institutions, then possibly they will be able to fulfill their requirement. But for the normal users who do not have access to general high performance computing machines, then what will they do? Then the only option is cloud computing. We don't have any other options at this moment. Like again, giving example of one of my students, he is working with GPU GPU version of set covering problem. On his own laptop, he could not experiment with many sets, right? Many elements and many sets. So he had to carry on his we don't have access to high performance computing servers. So he had to access Colab for running his GPU program for set covering, for parallel set covering problem. So that type of problem we are facing whenever we are working with high performance computing. So we have only one option at this moment, going for cloud, because we won't be able to purchase a high-end server at this moment. So anyone who will not be, and even if you purchase a high-end server, then also utilization is a factor. You cannot use you won't be able to utilize the high performance server for a long time. So these are the problems actually we are talking about. Okay. So if you compare with the price of the machine, maintenance cost of the machine, cloud cost of cloud will be much lower. Another question, I believe.
Okay.
Any question?
In chat box as well, we have a question.
Do you have?
How reliability improves from cloud to HPC on cloud structure?
I am not getting it. Sorry, what is the question?
Reliability improves from cloud to HPC.
Cloud to HPC. Chat is, I cannot load the chat. Cloud to HPC. Improve cloud to HPC.
Ma'am, I typed that. May I ask verbally?
Please ask. Please ask.
Ma'am, when
Yes,
you
yes,
were
sir.
showing the where you were showing that graphics, that wonderful graphics, that layered structure of, first you showed the layered structure of HPC, then you showed the layered structure of cloud, then finally you showed the layered structure of HPC on cloud. That was the third infographic. Now in the first infographic you said that HPC is very reliable, but the other things are difficult. It is more costly and all. Then when you went to cloud, you said that cloud has mostly positive features, except for reliability, because we do not have control of the hardware. Then when we went to the hybrid model, you said that finally the reliability problem is solved when we work with HPC on cloud. So my question was, how did the reliability problem get solved? It is still on the cloud.
It is still on the cloud, but this particular solution, whoever is giving the solution, this solution is being addressed. I mean, see, there is the hard money, because we have Hadoop, which is supporting for providing fault tolerance. So that fault tolerance, or you can have, because you have gone for cloud, so such type of tools can be developed on top of in the cloud, which can be used by the HPC as well. You see this particular, can you see the slide now?
Yes, ma'am. Yes, ma'am. This
Ah.
is the hybrid slide where you were showing us.
So this
The hybrid model.
this solution is provided by a particular company who is giving this solution, like Hadoop fault tolerance is being used by HPC part as well. Okay, so instead of Hadoop fault tolerance in cloud, actually you can create a tool. You don't need to rely on third-party tool. See, HPC means HPC machines. Traditional HPC machines are mostly proprietary machines with their own, other than if you have clusters, Linux clusters, Beowulf cluster sort of thing, then that's fine. But Beowulf cluster doesn't have any kind of fault tolerance. If you have proprietary machines, then either you will have to rely on third party fault tolerance, or uh, the particular company will have to give you the fault tolerance solution. But that's not, that till now that's not there till date. So here actually cloud itself provides kind of tool which will provide the fault tolerance mechanism. Because as I said, see, cloud can has the ability to migrate your task to some other uh, VM, right? It can anytime. Suppose you are using uh, AWS, right? Now at some point of time your VM has crashed for some reason, but there is a mechanism, checkpointing and all mechanism, to store the data and then move this to the uh, to another VM, which is created at that particular point of time, and it will continue your job. So that kind of fault tolerance is there. So it is reliable. That is what I'm saying.
Okay, madam. So basically, it is one more added framework that is providing the reliability.
Yes.
That Hadoop framework is providing it. Okay, thank you, ma'am.
In this case, yes. In this case, in this particular solution, it is Hadoop framework. Hadoop is providing.
Okay.
As I have shown, the Google Cloud, they have given a data proc for porting from traditional HPC to, so it's a similar kind of concept is given here. Okay.
Thank you, ma'am. Thank you.
So shall I start now or just 5 minutes? I'm unable to refresh here.
Ma'am,
Hmm.
will you take 5 or 10 minutes break? It's a continuous session. That's why you have to consecutive session.
Sorry, how many minutes?
Ma'am, according to your choice.
5 minutes, just 5 minutes.
Just 5 minutes.
Just
Okay, ma'am.
I'll be back by
Okay.
now it's 2020. I'll be back 2025 or 2020. Okay.
Okay, ma'am.
Taking just 5 minutes break. Get it. So the internet link is shared. Actually, this is the feedback link. Please fill the and phone number Otherwise, your attendance or feedback won't be met. So we will start the next session soon. Thank you all.